Welcome to the Boring Climate Podcast, a platform where we encourage serious climate conversations. We are fairly aware of the seen effects of climate change higher temperatures, melting glaciers, forest fires, sea level rise. But over the past 2 decades, NASA satellites have been documenting a quiet crisis taking place underground. As the planet gets hotter, people have increasingly drilled into a largely ungoverned resource of fresh water, those found deep underground. Joining us today from Calgary, Canada, is Dr. Hrishikesh Chandanpurkar, lead author of a recent study that uses over 20 years of this data to explain how human overuse of groundwater is dehydrating the earth and contributing more to sea level rise than the melting ice sheets. Rishikesh is an Earth system scientist working with the Arizona State University and focuses on studying water cycle changes at multiple spatiotemporal scales. He investigates their climatic and human causes and their impacts on socio-ecological and climate systems. With a PhD in Earth System Sciences from the University of California, an MSc in Environmental Sciences, and a BSc in Geology from the University of Pune, he has conducted research at NASA, Caltech Jet Propulsion Lab, the Department of Aerospace Engineering, and the University of Colorado. He was also a fellow at the Flame University in Pune and worked with the Global Institute of Water Security in Canada. Welcome to the show, Rishikesh.
Thanks, Vishwada, for inviting me. Happy to chat about the study and the state of climate and water.
Great. So we'll start off by setting context for our listeners. One of our most popular understanding of climate change is that a heating planet causes glaciers and ice to melt, and that leads to a rising sea levels. But your research kind of adds another layer that the global landmass has been losing its stored fresh water, and that the more we pump this groundwater, the more global sea level is rising. Could you start us off with what these sources of stored freshwater on land are and where they lie in the hydrological cycle?
So, thanks for ending the question with a hydrological cycle, because the water cycle that we've all studied in school uh, can be categorized, there into two sort of water cycle variables. So some of them are called fluxes, so precipitation, runoff, evapotranspiration, they are moving, right? So they are called fluxes. Whereas there are other variables that are stored variables, so storage variables, like lake is sitting there, right? Groundwater is again a stored variable. Soil moisture is a stored variable. Even river, even though it's moving at any given point, it has some volume which is always there, so that's a stored variable as well. Snow, when it snows in winter and it melts in spring, for that season that snow is stored. So these are called storage variables, and these form, if we add them up together, we are calling them terrestrial water storage, like TWS in this study. But essentially, it's just integration of all the storage variables. So you can think of land as a small buckets, and we are just adding these buckets together.
Right. And if we zoom in, what would constitute groundwater?
Right. So groundwater, you know, we humans have made these categories, right? But water is a very uh, transient uh, element. It keeps changing its shape, its size, right? And so uh, over land, everything starts as precipitation, right? So when it rains, some of it evaporates, some of it runs off, and some of it infiltrates into the ground. Now, when it infiltrates into the ground, it can stay at the soil, and become soil moisture, or it can percolate further down into the water table and become a groundwater. And groundwater can either, again, sit there depending on how the characteristics of the rocks are, or it can move. Maybe there are fractures or cracks through which it can move, or the rocks may be porous enough for it to slowly move. Uh, then there are, but it's not hard and fast. Like, so it can rain, like in the Himalayas, for example, it can rain. That rain immediately becomes groundwater, and then it is following uh, the terrain and can become a spring. So these definitions keep changing.
Right. So one of the things that made me click on your study, and I'm sure a lot of other people click on your study, was this finding that groundwater runoff is causing more sea level rise than glacier melt, which kind of upends what we traditionally know about sea level rise. If we were to compare the amount of groundwater that is causing sea level rise and the amount of glacier melt that is causing sea level rise, how would you do that?
So it's comparable, because so when you say glaciers, there are sort of uh, cryospheric process. We are talking about three things, the Greenland ice sheet, the Antarctica ice sheet, which are separate continents in themselves, and then there are mountain glaciers, which are over the big landmass, right? And uh, Traditionally, in sea level, half of it is caused by just increase in the temperature of water, like ocean water. So it's called thermospheric expansion. Half of it is caused by adding of water from the continents. So this includes, the ice sheets, Greenland, Antarctica, the glaciers, and the rest of the land. And now, traditionally, the rest of the land is all clubbed together as a single entity, and the total contribution from it to sea level is usually very low and has high uncertainty. But what we show here is that within this non glaciated land, there are regions that are drying and regions that are wetting. And if we look just at their individual trends, they are huge. So the drying trend that we see is much more than the glaciers, right? And the ice sheets, individual ice sheets, by the way, not clubbing them as together. Now, in this total, like loss from non-glaciated land, we find that 68% is groundwater. When we do the math, it is comparable with what we see in the mountain glaciers.
Right. Right. Which actually brings me to another question that I had. This 68% of freshwater loss is one of the things that kind of comes up in your study. How did you derive that percentage? And in simple terms, what does that number mean?
Right. So that's a great question. So our study focused on satellites, right? So the satellite is very simple. It tracks the changes in gravity uh, as the satellites fly over on their orbit. Now, gravity, water is very heavy. So month-to-month changes in water are they have a strong signal, and that's what we can track. But these satellites give us only the total water storage. It doesn't really partition it between groundwater, soil moisture, and all. And that's where models come in. Uh, there are land surface models. Some of them are better than others. Uh, Typically, models are not very good at simulating subsurface hydrologic processes, meaning they're not very good with groundwater or soil moisture. A lot of them don't have the soil depth that is realistic. uh, but then there are sort of amendments that are made. For example, they may be calibrated against observations and things like that. So we found a model which was assimilated with grace observation, meaning when the model was being run, it was incrementally being shown that, hey, this is what the observation is telling you, and so it was trying to adjust it such that it was closer to the observation, but at the same time fulfilling the model physics. It wasn't just, oh, this is the new data, I'm going to just become that. No, like, so it was trying to sort of optimize both of them. That's data assimilation. So we found a model which had that. Another model had better surface water dynamics, physics integrated into it. And so using these models is what we were able to isolate these different components.
Right. And in simple terms, what does it mean? So when you say 68% of fresh water is lost, what does that mean for the layperson?
Oh, I see. So yeah, so well, you can think of water cycle as a bank balance, right? So think of India, for example, and imagine India is a person who has a business income, right? And we get monsoons for what, like 3 or 4 months, and the rest of the year is dry mostly, right? So imagine having a business model where you are getting your yearly income in just 3 4 months, and for the rest of the months you have to sustain it, right, somehow. So you have to limit your expenses. We have to ensure that it is stored in an appropriate way, right? If you are good at that, then over time you will see your bank balance is increasing, right? Your net worth is increasing. What we are seeing here, like, when I say that we are experiencing a freshwater loss from all the continents, is all the continents are losing this bank balance. So after accounting for their income and after accounting for their expense, the net is a negative cash flow, with such that the bank is losing water, the bank is losing money every year for the last 22 years, right? Like, on an average. Uh, yeah, so this is significant because this suggests that this is not sustainable.
Right. Before we dive into your study further, could you kind of explain to us why groundwater is significant, the role it plays in supporting different ecosystems, and the regions or communities that are most dependent on it?
Right. So this is actually extremely important for India because, as I said, India gets only the most of its precipitation in like 3 to 4 months. The rest is actually sustained by groundwater. So groundwater is, you can think of it as a hidden storage. It's hidden, unfortunately, so we don't realize how important it is or how big it is. So we don't really know how much water is stored, say, under Indian land, right? But uh, we know where the groundwater aquifers typically are, uh, and the importance of them is, it is literally what sustains everything in India. Even the Himalayas, the springs, the nalas. I did my master's thesis in the Himalayas, and Himalayan rivers are glacial fed, right? But even there, groundwater plays such an important role in day to day living. Like, life would be impossible without groundwater. Uh, uh, in the semi-arid region, which most of India is, groundwater plays a crucial role in supporting the ecosystems. Whenever you see water in the river, despite it being a non-rainy season, it is supported by groundwater. So it's kind of a misunderstanding that the rivers and lakes, the surface water, is supporting groundwater. It's actually a very dynamic system, and oftentimes the reason that we see a lake is because the groundwater is supporting it, right? So it's extremely important. It touches all aspects of life, especially in India.
Right. And so when it comes to the impacts of climate change, so two questions here. Does groundwater or any of these terrestrial water sources that you mentioned, do they provide us a buffer against the impacts of climate change? And second question, how sensitive are they to climate change?
Yeah. Okay. So this is really good. So yeah. So groundwater adds persistence to the system. So when I mentioned, water cycle, it rains, some of it runs off. That happens instantaneously, right? Evaporation also happens quite fast. Groundwater, because it's hidden, and because it goes to depths that are not known, and uh, the water would sort of pool together in places from different places. uh, it adds this persistence to the system, because of which it slows down the changes. So if something is happening very fast, it will slow it down. And that is very important because it gives us time and resources to, in an event of a drought. That's typically the where we would get more water from, and it's sustainable in that way. Uh, yeah. But and how sensitive to climate change it is? That's a great question. So uh, one of the things with climate change is, of course, increase in temperature, right? Another is also changes in precipitation. So some places, like dry places, are getting drier, wet places are getting wetter. uh, in general, we are seeing this dynamics between evapotranspiration and precipitation changing at climatic time scales. So because of that, what happens is when precipitation decreases, the first thing is, the soil gets dry, the plants start drying. So this is all sort of, first it's atmospheric drought, then it becomes agricultural drought. We see crops needing more water. Ultimately, after a few years, it would become a groundwater drought. So we would lose groundwater from climate change. It will take time, so it would kind of be the last soldier to fall in this sense, right? But it is sensitive, right? Especially to prolonged droughts. Uh, and that's something to consider, so it as a last resource is a great option, but if we are using it as our primary water resource, which a lot of us are doing, that's not great.
Right. So we'll get into your study a bit more now. You examined 22 years of data from the NASA Gravity Recovery and Climate Experiment satellite, right? What were some of the most critical revelations with respect to groundwater levels and its impacts on land and sea?
Right. So yeah, so this study was more holistic, right? Like, so it was looking at the total water storage, of which groundwater is an important component. We attribute 68% of changes to groundwater, but overall, in apart from that statistic, global statistic, we don't really delve into uh, which region has how much groundwater changes and all, because even though some regions obviously, like the total water storage signal we see is from groundwater. But what we see in this study is globally, freshwater storage, in all these forms, is being lost from almost all the continents. The regions that have been drying, that are typically dry, arid regions like mid latitudes, like 30 degrees north, right? They are losing water at unprecedented rate. Uh, some regions which are wet, like in tropics, they continue to get wet, but this is mostly uh, related to Africa, and it's because of natural climate variability. So it's not really, uh, climate change adds to it, but it's not really driven by climate change at this point. Uh, but the drying regions are, they show very low year to year variability. They have a very strong, very robust long term trend. The polar regions are also seeing this trend, and as per climate models, the precipitation in the polar region should increase, and so these places should get wetter. uh, what we are seeing from grace is that these are losing mass, so permafrost thawing, glaciers melting, and so on. So that is one. Another important thing is the regions that have been drying, which were previously identified, they were like hotspots of drying, like in North India being one of them. Uh, they are now connecting with each other because the land between them, uh, which researchers would typically ignore because the trend was not very strong, uh, is the trend is becoming significant enough that we are seeing this big swaths of drying regions, and we call them mega drying regions, and there are four of them that we have identified based on our robustness analysis. uh, and India is being a part of it. So the MENA region, which is Middle East and North Africa, Europe. So, so this is really a tri-continent, like three continents uh, drying together. And it's huge. Like if you see like 40 degrees north, from British Isles to East China Sea, the entire landmass is dry.
Right. And specifically, so you mentioned the northern part of India. Which would you know which states are maybe most impacted by or are part of these mega drying
Right.
regions?
So these include northwestern states. So Rajasthan, Punjab, Haryana, Uttar Pradesh, Uttarakhand, Himachal Pradesh. We are also seeing some drying in Bihar, Arunachal Pradesh, West Bengal.
Right. And could you kind of briefly take us through the losses that India is suffering or would suffer because these regions are part of the mega drying zones?
So India, the hotspot over India is primarily driven by groundwater. So this is, monsoon has been changing, but this is a very steady, hotspot in regions which have been producing, a lot of, agricultural productivity in India. And uh, at some point, it's going to be difficult to get to that groundwater, right? So financially, physically, right? So technologically, uh, then what would we do then, right? So that's the question. And so far, the rate at which groundwater abstraction is happening, it is not possible to replenish it uh, from the rain that we get every year. You know, so it's too fast and too much. And so in terms of water mitigation and water sustainability, we are really headed towards water bankruptcy in India.
Hmm. Yeah, which kind of brings me to another question that I had is, um, the most critical finding of this study is that the mined groundwater rarely seeps back into the soil and instead is running off. And the second thing is that all of these aquifers took millions of years to form and therefore are not easily going to get recharged. So, if these trends cannot be reversed, what scenarios do you maybe foresee for coastal regions, which would probably face the brunt of rising sea levels?
So coastal regions, so there are kind of two aspects here: sea level and groundwater, and of course their connections, right? Unfortunately, uh, sea level is a global problem that is dependent on mitigating the greenhouse gas emissions. And so far the global efforts haven't been as great, especially in times. And so coastal communities need to uh, start doing adaptation measures for this, because sea level is rise is going to happen. It's not going to happen uniformly at each location. So a lot of cities like Mumbai, for example, they have a climate action plan, sea level features in sea level rise features in them. And so it's they should be bracing for that. Now groundwater, when it adds to this, right, a lot of groundwater that is abstracted and being added into the ocean. There is also places that are wetting, so the net effect of groundwater being added to sea is not as much. you know when we were discussing earlier, we were talking about the drying regions and why it's important, because it's actionable, right? When we are pumping groundwater, it's an action that we can stop, right? Uh, but there are regions where it's raining more and they're getting wet, and so there's increasing groundwater. So the net groundwater contribution to sea level is uh, is is significant, but it's not as much as just considering the drying component. Okay, uh, but again, it needs to be dialed down. Also, when the groundwater is being pumped near coastal regions, it creates sort of a vacuum within land, and the seawater gets in. It's called saltwater intrusion. It is really destructive for the plants and for agriculture and just everything, because it's salty water, right? Uh, and so these are kind of con- connections between groundwater and sea level that coastal communities should really consider and be aware about, and have them in their adaptation plans.
Right. And so this kind of study takes us one step closer to understanding something that we don't see. But in your view, how do current climate models, both Indian and global, fare in predicting underground water trends and their impacts on global systems?
Right. Hmm. So, uh, unfortunately, uh, models don't do a good job, with groundwater. Because, see, a model is, uh, like, if we know something, only then we can put it in equations and have it as a model, right? uh, Globally, even groundwater depth, water table depth is not known. The soil depth is not well modeled. A lot of them have just a uniform depth, and it doesn't make sense. So a lot of them don't really do a good job with subsurface hydrologic variables like groundwater, even soil moisture. Uh, However, there are tricks that modelers use, by maybe calibrating their results with observations wherever they can find, uh, or relying on other calibrations. Like if you have precipitation and if you have uh, runoff observation, if you have some understanding of temperature, then you can sort of parameterize is something, when you don't know the process, you just represent it with a number. And so we don't really know what's going on underground, but hey, if we put it as X, then everything makes much more sense. So do tricks like that, which is fair. They have their strengths. And so but typically, when we talk about climate change models, climate models projecting into the future, we see changes in temperature and precipitation, and that would typically direct how groundwater would look like. Also, the human dimension, where there would be more water demand, less water demand. There are these scenarios, which in which, like, for example, regional rivalry happens or things like that. And so uh, but what we are seeing globally, by through climate models, is the places that are drying, places that are dry will get drier, places that are wet will get wetter. There will be changes in precipitation and temperature globally. It will be asymmetric, but it would happen, and it would trickle down into groundwater.
Right. We'll now kind of move into the implications of these findings in real world scenarios. And one of the things the study kind of warns of is cascading effects, right? So food crisis and water conflicts and things like that. In your view, what kind of governance or policy measures could help us prevent these crises?
Yeah, so that's a good question. So I think, uh, when forming policies, right? Like, so I guess, everything comes down to the sense of belonging. Like, for example, we care as individuals, for ourselves, then we care for our family, right? Then we care for our community, uh, because these are common pool resources. you know the sense of belonging is very important. Like, do we have the sense of belonging that we, like India as a country, as one community, should be conserving its water, right? Do we have that sense of belonging, whether we as South Asia, right, like including countries which are neighbors, right? uh, uh, Whether we are sharing, because these are transboundary systems, so they don't really go by the lines that humans have arbitrarily formed, right? And so whether we can uh, consider this as a common pool resource, then, can we do it on a global scale? So it all comes down to sense of belonging. And uh, the more people interact with each other, the more they understand each other, the more they try to build on the things that they agree upon. I think that's crucial. And I know this is not related to water, but it is, right? And so this is where the resilience will come in.
Right. And in terms of further scientific interventions, or even policy interventions, what would you say might help reframe water as, like you mentioned, it's a finite community, it's a intergenerational resource. What would help reframe water as this rather than just a commodity that we use and forget about?
Right. So I guess water is a necessity, right? Everybody, it's a right, human right, but it's also a luxury, and so that is something to remember. And so again, water as a finite commodity is a very important thing to understand, because since school we have been taught about the water cycle, and hey, it's going to rain next year anyway, like we can spend water. So that's not necessarily going to happen. And uh, so first thing is, of course, awareness, right? And second is understanding, the value of water in ways that uh, in the sort of the same currency that you apply to other goods and commodities. Now, pricing of water is an important topic in itself, but it's important. Water tax, I think, I think Karnataka government introduced groundwater tax recently or something like that. And so I think that these are like really good first steps towards acknowledging this as an important entity which is supporting everything, right? And so going ahead with that, so we are also collaborating with the World Bank, uh, and uh, like a flagship report based on our studies, which would also include a lot of policy suggestions, and solutions would come out, will be coming out soon, I think in October. And so there we discuss this all this in more detail.
Right. And, final question. If we were to sum it up, what would you say is the most accurate way to explain the chain from groundwater pumping to land drying to rising seas and coastal flooding? And, if we were to frame a narrative this way, would that maybe help near term policy change?
Right. Well, I think, but the more accurate narrative would be, precipitation decreasing, so either from climate change or from natural climate variability, like the droughts, which would stress the surface water systems like dams, right, and reservoirs, uh, which encourages people, or even lack of irrigation, right, surface water irrigation, and which encourage people to use groundwater, which then ends up uh, in the ocean, and which causes sea level rise. Uh, I think that's kind of a more sort of, I guess, chronological way of looking at it from a land perspective. Yeah.
One of the questions was actually if how you decoded the grace data.
So Grace actually does not. It doesn't have a camera on board like the way Landsat has. So it's not optically seeing changes. What it is, so there are two satellites of Grace. One is called Tom and another is called Jerry, and they are like moving one behind each other, right, uh, in the same orbit. And the the cool part is the distance between these two satellites is measured really accurately. Uh, and so what happens is when the first satellite, Jerry, I guess, if when uh, it sees a mountain. Mountain has a lot of gravity, right? So it gets pulled because of that gravity. And but Tom, the satellite which is preceding, hasn't felt that pull yet. So the distance between them increases, and then so these changes in the distance between them is how that distance is then converted into gravity anomalies in a way that would make sense. And then they have to filter out a lot of things, like maybe there is a movement in the mantle, maybe there is some atmospheric dynamics going on, maybe there are regions on earth where which used to be glaciated, and the glaciers have gone but the land is sort of coming back up. So things like that, so they are all sort of filtered, uh, and then generated as water anomalies. So earlier, this used to be a tedious process, which even hydrologists would have had to do. But nowadays, they provide solutions that are very easy to use. So you can literally just these are like monthly maps of how much water has changed. So it's
Nice. Okay. Right. Great. Okay. So we only have now the rapid five questions.
okay.
Right. So the first question, is there a continent where freshwater loss is not happening, or where the land isn't drying?
Right. So yeah, so drying is happening in all continents we see, but if we also include the regions that are getting wet, then Africa stands out as the only continent where things are getting more wet than dry.
Right. Top three human activities that you think are causing the most groundwater loss.
Right. So agriculture is really the biggest, Then there is, of course, industry. There is also nowadays, just municipal water consumption is also an important thing. Uh, yeah, I guess you said top three, but I think electricity generation, yeah, is also another. There are a lot of ways.
Which parts of the world contribute the most to the drying signal that the GRACE satellite caught?
Right. So, so the tri-continent mega drying region, which is, it includes Europe, it includes North Africa, it includes Middle East, it includes Asia, South Asia, and East Asia, Central Asia. That is definitely the biggest one.
And would you say drying areas are growing faster than areas that are wetting every year?
Yes. So the intensity of drying is so both are the intensity of both are increasing, but drying areas are getting drying faster than wetting areas.
As researchers, how do you know that land water losses are large enough to raise sea levels?
Right. So this is actually so we have independent observations, right? So we have satellites that are looking uh, at the sea level height. So they bounce radar of the satellite, and it comes back, and they measure, so they know the sea level height, like the sonar thing that we learned in school, right? Uh, uh, but there is also, so that is altimetry, and it's like the observations are since 1993. uh, we have another component of sea level, as you know, is thermostatic expansion. So there are these sort of machines, not machines, but I guess automated, units called Argo, that are like, there are thousands of them in the oceans, and they have been measuring temperature, salinity, and all these things. And they also see, so they can more or less accurately tell us about how much the temperature is changing, and because of that, how much the height would change. So these are from the ocean. Uh, and then over land, we have grace observation, which gives us gravity, so actual volume of glacier or ice loss, as well as freshwater loss. And so through these, we get a fairly good understanding of what's happening. You know, and it's literally, like, so in the water cycle, there is atmosphere, land, and ocean. Where atmosphere holds really less, very very less water. So it's really a thing about just two buckets, land and ocean. And so when because water is conserved, whatever are the losses from land, they ultimately get into the ocean.
Reach the
Yeah.
ocean. Right. That's it. That kind of sums it
Yeah.
up. Yeah. Thank you so much for your
Yeah, of
time,
course.
Rishikesh.
Yeah.
This was a very insightful
Yeah. Thank
conversation.
you. Thank you. Wish.